Welcome to the Professor's Du Bois channel. We're going to continue on with our lecture series for General Chemistry 1. And in this lecture, we're going to be talking about the percent composition by weight of elements in a compound and how to calculate those percents if you have the formula, and then also how to get the formula if you're given the percents.
That sounds like a lot. We better get started.
We better do it.
So the percent composition, we're going to find the percent by mass of an element in a compound. So the example here, we want to find the percent of hydrogen in H2O, or water. And the way we do this is we take the mass of the element that we're looking at, and we divide by the total mass, and then multiply by 100. That'll give us our percent. So in this compound, we have two hydrogens. So we're going to have to take that into account. We have one hydrogen that weighs 1.008. So we're going to multiply that by 2 to get the total mass of hydrogen in this compound, which is 2.016. And then we're going to have to add the mass of the oxygen to get the total mass, which is 18.015 grams. So now I've got the mass of the hydrogen, that's what I'm looking for, divided by the total mass, 18.015, times 100, and that ends up being 11.19% hydrogen. And it's a little bit surprising because there's two hydrogens and just one oxygen, and it's a very small percent, but this is percent by mass, and hydrogen's very, very light. So this is, it may look surprising at first, but if you think about it a bit, it makes sense. So
how about the percent of oxygen? How could we calculate that?
Two ways we could calculate that. We could go through the same routine. We could take the mass of the oxygen, the 15.999, divided by the total mass, 18.015, times 100. Or, much easier, I think, is since there's only two elements in this compound, and we know the percent of one, then they have to add to 100. So I could take 100 minus 11.19 and get the percent oxygen. And that's pretty common to do the percents of all the elements in a compound.
Or you could do it both ways, add them together and make sure they add up to 100. That'd be like a little check.
Yeah, it'd be a good check.
Yeah. All right, so continuing on, getting from from the formula into percent. So here's another example. So what's the percent oxygen in potassium permanganate? And I want to point out here we have 4 oxygens in potassium permanganate, and that mass of oxygen includes all 4 of them. So you have to multiply your mass of one oxygen atom from the periodic table by 4. And then you have to also figure out the entire total mass of the compound, which is the molar mass. So in this case, one atom of oxygen is 15.999. I get that from the periodic table. Multiply it by 4 because of 4 in my formula. And this is the molar mass of the entire potassium permanganate compound. Multiply that out, multiply by 100, and you get 40.almost 5% oxygen. So this is the next thing that we can do with percent by mass. So we can get the empirical formula, which is the smallest whole number ratio of the elements in the compound from those percents. So we're kind of doing the opposite. So this example, find the empirical formula if you have the percents of potassium, sulfur, and oxygen. So what are we looking for? We want a formula. So the formula means we have some number of Ks, and we're going to use our subscripts there for our Ks. We have some number of sulfurs, and we're going to have a subscript for that as well, and we're going to have some number of oxygens for this formula. So we need to know what the ratio is here. How many Ks to how many S's to how many O's? And this sounds like a single ratio of numbers if you just had one compound, but if you have an entire mole of compounds, these subscripts turn into mole-mole ratios, and that's the key to solving these. We have to find the mole-mole ratio of these elements to each other. So if we need moles, we know that we can get moles from grams. So that's the trick. Turning these percents into grams. From grams, we can convert to moles. Then we'll have our ratio.
So how are we going to find the mass, though? I mean, all they gave us was a percent, and I don't even know, how much is there?
Right. So there's a trick to that. If you assume you have 100 grams, if you have 100%, you have your percents. If you assume 100 grams, then each of those percents turns into grams, and then we can convert our grams to moles from there.
I see. So 49.41% of 100 grams would be 49.41 grams.
Right.
Nice.
Right. And the formula is going to be the formula regardless of how much you start with. So we can assume 100 grams. Makes it easy. Makes the math easy.
We like to make chemistry easy.
We do. Yeah. First step is to convert our first element, which is potassium, K. This 39.098 came from the periodic table.
Molar mass.
Molar mass of the one atom or 1 mole of potassium. And so now we have our moles of potassium. We're going to do the same thing with the other two. Again, molar mass from the periodic table. Now we have a mole-mole ratio. We have a formula, right? So we can put these moles, right? You said it was going to be a subscript.
Yep.
Is that right?
Well, it's not right, but it's a good start. I mean, we're on our way to having this, so
we're close.
But we need to have whole numbers. So we're going to have to somehow convert these into whole numbers, and it's easier than you'd think. So what we do is we take the smallest one and we divide everyone by that smallest number. So since we're dividing everything by the same number, it's okay. It's going to be
same
fine.
ratio. Yeah.
So if we divide 0.6319 by 0.6319, we get 1. So we've got a whole number there. And in this case, the others happen to be whole numbers as well. So now we have the ratios. We have K2, S. We don't write the 1. Just the symbol represents 1, sulfur, right. And O3. So there we go. Yeah. There's an empirical formula, and we just started with percent by mass. Now, sometimes they're a little more tricky.
They are, yeah. So you're guaranteed to get one of them to be a whole number. That's the point of dividing by the smallest one, because anything divided by itself is going to be 1. But sometimes you do the division, and then you have the 1, but they're not all whole numbers. So if that happens, you have to multiply all of them by a factor. Just like dividing by the same number didn't change the ratio, multiplying by a factor doesn't change the ratio. As long as you multiply all of them by the same thing, you're going to end up with the same ratio. So if after you divide by the smallest, you end up with something that has a 0.333 at the end, you're going to multiply by 3. Because that would turn that into a whole number.
Multiply everything by 3 in that case.
Every single one, right. If one of them ends up being 0.5, you can multiply all of them by 2, etc. So for this example here, after dividing by the smallest one, if you got, for example, iron to be 1, that was our smallest one, but oxygen turned out to be a 1.5, you can multiply by 2, because we had one that was 0.5 something. Now we have whole numbers. We have 2 irons to 3 oxygens. Our empirical formula is Fe2O3, and that's the smallest whole number ratio.
So empirical formulas don't always have an element with just a subscript of 1.
No.
Sometimes they do, but not always.
So pause the video and try this one. From the percents, so you have two elements, and try to get your simplest whole number ratio, which is your empirical formula.
So percents to mass, assume 100 grams, mass to moles, and then divide both by the smallest number.
And you should have gotten NH2 for your empirical formula. And that sometimes is the answer to the question, what is the empirical formula from the percents? But sometimes you need to find the actual formula. So when we have an empirical formula of NH2, the real formula might be any multiple of those. So it might be N2H4 or N3H6, etc. So if the question asks for the actual formula or the molecular formula, you need one more piece of information, and the problem will provide that. So it will provide you with the entire molar mass. You calculate the empirical formula, and from there you have to figure out what that molecular mass is. Sorry, the molecular formula is. And the way that you do that is calculate your empirical mass from what you just calculated, and then the given molar mass you're going to divide to get your multiplier. How many of those empirical formulas fit into the actual formula? That's the multiplier.
So in this case, our empirical mass was 16.02. That was from the NH2. And they said that the molecular mass, or the molar mass, was 32.04. So I took the 32.04, divided by 16.02, and got the number 2. That's my multiplier. What that means is I'm going to multiply everything in my empirical formula by 2. So I had 1 nitrogen, now I have 2 nitrogens. 2 hydrogens becomes 4 hydrogens. Now, there's another kind of a brute force method of doing this. Like if you have an empirical formula, you know what the molecular formulas could be. You could just multiply everything by 2 and then times 3 times 4. And then you could just calculate the molar masses of these potential...
Sure. Just trial by error.
Yeah. It's
you
kind of
figure it out.
You could do it that way. It's usually much easier to just use this multiplier.
Just divide. Yeah. Yeah. So that wraps it up for percent composition and determining the empirical formula from percent composition. So hopefully that was helpful to you, and stay tuned and come back for our next video in the series.
Thanks.
Bye-bye.